Right. So we mentioned there are many other software, data processing software built around MapReduce and HDFS. And two classic examples are, actually, we probably should say three examples are the Hive, Peak, and Spark. Okay. So what are they? We briefly mentioned it before. For Hive and Peak, they are the language, right, on top of MapReduce, because MapReduce still is a form of program. You have to write those function code, right? And you have to know how the MapReduce programming model looks like, and so you can convert your algorithm to the MapReduce program. So you still require a lot of knowledge, knowledge, right? And you have to figure out how to convert the algorithm on your own. So as we mentioned, for the trend of big data processing, people prefer to use the language or the interface, programming interface they are familiar with, such as the query language, right? Or the data flow language. So Hive is the provide the query language. Specifically, it's a query-like, SQL-like language. It's not exactly the same as SQL query, because at the end, what's behind Hive is not the traditional SQL database. It is a NoSQL database. So it's a distributed database. So some of the features like the join or other operation that may involve communication across servers, those operations are not supported at all by the underneath NoSQL database. So therefore, of course, the query language also doesn't support those operations like join. Right? So, but for other operation that supported by the NoSQL database, of course, the query language will looks like the same. Okay, so that's why it's called a SQL-like language. Okay, and in other words, through Hive, the programmer, the user, only need to be familiar with the SQL language, and then they can describe their data analytic job or their data analysis operations by the SQL query, and then run on a distributed system through a data processing framework like MapReduce. Okay? Similarly for Peak, right? It's actually again it's actually it try to mimic the Peak logging language. Okay, the Peak logging language is a data flow language, um, because for most of the time when we try to do the data analytic work, um, what we describe is how the data is flowed through some operations. Um, for example, TensorFlow, as you might heard, and we will talk a lot more in the last lecture in this course. It is a typical data flow language because TensorFlow, the tensor stands for data. So even application like deep learning, its computation is actually can be described as a data flow. So many language specifically designed for data flow processing. So we will see an example of a Peak, but you can tell that the way he write is a script language, and it also try to describe the process based on those data flow. Okay, right. So this is also very well known for data analytic jobs. So again, people would like to use those data flow language instead of the MapReduce program. So we have this Peak project to support that. So you can write this data flow language like you used to, but this program will actually generate into a set of MapReduce jobs and to perform the actual data processing work across a distributed system. Okay? So either way, those are the example that people try to provide the higher level language, right? To facilitate the large data processing and to reduce the programming burden or lower the shorten the learning curve. Okay, right. So you can see that MapReduce become the engine for those solutions. Okay, and this is the exact example for Hive and Peak. So for Hive, you can see this is pretty much a SQL query, right? You have seen, right? It looks very, very similar or exactly the same, okay? And but this will actually going through Hive to translate this query into a set of MapReduce job. It's not just a single job because this is a complex query, right? So you can imagine it requires probably several MapReduce job to process the data step by step and finally get the final results. Okay. Similarly, this is the pig script. So this you can see what we call the data flow language, right? Every variable here is a data, and you can see we always input some data and then through some operation and transfer those data into another data. So those transformation and how the data basically flow through those operations to generate the final results. Okay? So this is a type of data flow language. Okay? And so you can see this probably not too hard to understand or learn this language, right? Definitely much easier than the MapReduce to write a MapReduce program. Okay, so those are example that people would like to use when they deal with the big data. Okay, they don't want to learn new language or learn new tools. They just want to use what they because many data scientists they are right they are not engineer. Okay, so they are good at math but not necessary for programming. Okay, or engineering. Okay, so either way, for Pig or Hive, what happened is the whole program you wrote or the query will convert it into several MapReduce jobs, like showing over here. So in this case, the Pig script we just saw will actually convert it to all those map tasks and reduce tasks, and each color represent a MapReduce job. So you can see this example actually require 3 MapReduce jobs to complete the work. Okay, so you can see that's another reason why people don't want to write the write the MapReduce code by their own, because a single work might even need to divide it into several MapReduce programs. So it's not that straightforward, right? It's we want to write a single code or a single query, right, to do all the things. Okay, um, so that's why we have the Pig project and the Hive project to do the translation for us and try to convert those operation into a set of MapReduce jobs. Okay. So from there, you can see the problem of MapReduce, right? First of all, uh, it's a very limited programming model, right? A MapReduce job can only do map and reduce. That's all. Okay. If you want to do multiple maps, you have to write multiple MapReduce program and run multiple MapReduce jobs. Okay. And secondly, the input and outputs are all must be stored on a distributed file system or on a file system. So if you want to concatenate the MapReduce job, or if you want to pass the output of a MapReduce job to the next as an input for the next MapReduce job, you have to pass through the data. The data have to pass through the file system, means a disk I/O, right? So it's very slow, right? Because disk is very slow. Okay, so if you want to deal with those complex data analytic job generated by, say, Hive or from Pig, then um, it's very, very time consuming, and you have to manage several map reduce jobs. So it's not convenient and not efficient. Okay, especially after we have this big data concept, then people start to focus more on the machine learning algorithm, right? Once you are able to use MapReduce to reduce the data size, then people start, they will try to use those more complex machine learning algorithm to analyze the data. And all those algorithms usually are iterative algorithms, right? We know those are iterative algorithms. So that means every iteration, you have to run a MapReduce job. And you even have to probably write another MapReduce job or another program to determine whether you should submit the next MapReduce job to do the next iteration. So at the end, the user have to write program to control this computing cycle. So it's really there's a lot of efforts, and you have to write several code to do a simple thing or to do one thing. Okay, so it's not very convenient. And as we said, it's an iterative algorithm. So the output of the previous iteration will be the input of the next iteration. And if we have to write the data to disk and read it out right after, this is very time consuming as well, right? It will make the execution time become much longer. Okay? And also another limitation is we cannot handle interactive data analytic. So what is a interactive data analytic? That means it's exactly what happens when people use a solution like database, right? Usually we just submit a query and get some result, immediately get some result, and based on the result to decide what we want to do next. Okay, so it's an interaction between the user and the system. Okay, and usually, again, the input from the previous result will be used for the next processing task. So if we again have to store this immediate result to the disk, it will cost a lot of disk I/O. So that's why, and disk I/O is slow, and user cannot wait for that long. So again, MapReduce is just for batch processing. It's not for stream processing or for any interactive processing. Okay, so the tool need to be used right. The tool is designed for specific problems. So if this is not a problem designed for MapReduce, then if you use it, you will not get the performance, at least not the performance you expected. Okay, so you can see as we go to the top of data analytics, usually we will like to use those interactive or iterative algorithms. And all those algorithms are not fit for MapReduce. Okay, so that's why we have Spark, right? So how Spark solve it? It's actually quite simple. It's exactly what we have been doing on a single machine or in our operating system or our single machine software stack. Basically, we have memory, right? So the reason we have memory in the von Neumann architecture is because it allows us to store the temporary data, right? So we don't need to always read-write the disk. It's too slow. So we have memory to cache, to buffer our data, so we can support those interactive and iterative data processing. Okay, but different from a single machine, we are talking about a distributed system, right? So that means that memory needs to be spanned across machines. And also, more importantly, don't forget, the biggest problem of a distributed system is we have tolerant the failing, right? The machine in the data centers could fail at any time. And it become a challenge for a memory storage layer because we know memory is volatile, right? So if a machine fail, you must have a way to recover the content in the memory. Otherwise, well, the, the solution won't work. Okay, so the key innovation for Spark is to build this distributed shared memory layer, right? As its name imply, it's a memory layer, and the memory is shared across all the tasks across machine, and the data is stored distributedly across the machine as well. At the same time, the DSM needs to be scalable and fault tolerant to machine value and in an environment like a data center. Okay. All right. So its main contribution is actually about how to manage those memory, not about how to do the parallel processing, because that part is actually just simply borrow from MapReduce framework. It's pretty much the same. Okay. All right. So let's look at a bit more detail. So first of all, for the processing part, the programming part, it borrowed the idea from MapReduce. That is, we want to provide functional abstraction, right? The function should be all the operations should be abstract as function, and those functions should be able to independently apply on the record. So therefore, we can scalable, right? And we can avoid synchronization and communication across those machines. But MapReduce is a limited programming model because it only abstract the data processing as the map function and the reduce function. But in more general application, we might need other functions, right? Not just map and reduce. We could apply many other functions to transform the data, to process the data. So it's actually not new. A set of a language is called a functional language. It's called a functional programming language. So this class of a language try to define a set of functions and provide them as the API for the user. So the user basically apply those defined function on the data flow and to process the data and generate the results. Okay, and so Scala is one of the language in this class. It's one of the functional language. Okay, so for Spark, it decides to further generalize the programming language by simply adapt Scala as his programming language. So so basically, Spark, you can say it is a parallel execution engine for the Scala language, because Scala is used to run only on a single node, and he will still parallelize the computing across cores, but it's using the thread, not the process. Okay, so that's therefore the traditional Scala code can only run on a single machine with shared memory. But Spark it's actually an engine, so it will convert the Scala code into a set of processes and run across the machine of a distributed system. Okay, so that's so if you want to learn Spark, how to write Spark, it's actually much easier because all you need to learn is the Scala language. Okay, and this is the Scala function that is supported by Spark. Okay, not all of them are supported by Spark again because some of the function may require too much communication. So it might practical on a single machine, but it become non-scalable across a large-scale distributed system. So probably not all the all the Scala language are supported by Spark, but most of them. Okay, um, so those are some examples. You can see we have map, flat map, filter, etc. All those are the function defined by the Scala language. Okay, and so like the word count example we mentioned before, right? If we use Spark, all we need to do is to write this Scala program. And you can see you only need to write 2 lines of code, right? And it's a script language, so it's easy to read, easy to learn, right? But it has exactly the same effect of a map reduce framework. Because as you can see, the first line is try to read the files, right? And it will become, this text file will read the whole file and actually break the split, I should say, split the file content to a set of lines, okay? And so become this data set, okay? So the file after the first statement will become this data set stored in the memory. And then after the flat map, it will map this. As you can see, this map is simply just split the word of a line, right, to individual term. So this will convert this data set to this data set. And then this data set will go through the map function to, right, simply said, generate the key as the term, as the word, and 1 as the value. Exactly like what we introduced before for a map reduce, right? We won't have time to explain the syntax, the language grammar, but just trust me, what happened there for this is a abbreviation, right? So this is what happened is you will basically like the grouping reduce. Reduce by key means you group the records by their key and do the reduction for each key. So exactly what the reduce function perform in the map reduce framework. So the result, of course, will also be the same, right? You will aggregate the key together and apply the reduce function on the key and get this word count result. Okay. All right. So you can see in terms of the programming interface, Spark further generalize the interface for map reduce for not only support the map and reduce function, but all the functions that has been defined from a functional programming language like Scala. Okay, so it's more powerful as it's more easy to write as well, right? Okay, so that's how you can write a Spark code. Okay, we will just stop there and then switch gear to explain the most important part. That is how to build this, provide this distributed shared memory. Okay, so first of all, the data set stored in Spark is called the RDD. Okay, the data set is as you see over here. Actually, Scala is also a data flow language. So you can see every variable here represent a data set. Like we said, this is a data set, line referring to this data set. This data set has only 2 elements. And over here, the count is the result. So the count is this data set. And as a result, this count has 4 elements, right? With the type of a key value pair in this data set. So every function we apply is a transformation of the data set from its input data set to its output data set. So everything is data sets. Okay. So those data set is actually stored on the memory. That's why we can keep generate it and read it out and convert it right away. This all those things happens in memory, not on disk. Okay, so those data set managed by Spark are called the RDD, Resilient Distributed Data Set. And it has this name because this data set is just like the Hadoop file system. The data set is partitioned. And well, it's not replicated because it's just a temporary stored data. So it's not replicated across machine, but it does um, partitioned and stored on different machine so that the RDD can be very large, could be larger than the memory size of a single machine. So that's why he can handle a larger data set. But the data set that this RDD, the size of RDD is still limited by the memory size of your distributed system, right? So if your data set is really, really huge, larger than the aggregated memory of all the cluster nodes, then you still have to use a solution like the MapReduce, because MapReduce only rely on the file system. Okay, but usually we use MapReduce to pre-processing the data, right? To filter the data, to reduce the data size to a degree that can fit into shared memory provided by Spark. And then we do those machine learning and iterative data analysis. Okay? So back to this RDD. So you can see it's partitioned, and also it's immutable. So why is it immutable? Because if it's immutable, then we don't need to handle all those synchronization problems, right? Because it's a read-only data. So no one can modify it. So no, we can allow concurrent access to the data set without any locking or synchronization mechanism. And also, if we want to rebuild the data, right? Because we have to torrent the value, that's the most important part. If we want to torrent the value, all we need is to store the transformation function. We don't need to store the data, because if we have this function, right, basically your code, we can always generate the same result from the data source, right? So because it's immutable, so we don't need to keep any version problem. We don't need to do versioning. We don't need to remember what data is manipulated over time. All we need to is to remember the transformation function that generate the data set. Then we can always, if some data set, for example, maybe this one, maybe this data set stored on some machine, and that machine failed, then Spark can regenerate the result from this data set, right? If we have this data set stored in other machine, we can use this data set to apply this function and then generate the missing data set. Okay, so we can always regenerate it from the previous data set. Okay, all right. So so that's why RDD also is resilient. It is resilient to failure because you can always regenerate it from the function of your code. Okay, all right. And a bit more detail is that actually the data set we mentioned over here are not always materialized or stored on the memory. The reason is because imagine we could do that. We could store every data set in our memory. So if we want to rebuild, we can always just trace back one step. However, it will waste a lot of memory space, right? Memory is still very expensive, very limited. So if we do a word count, we have to store 4 data sets in the memory. Then we consume 4 times of the space. So it's not very efficient. So in fact, whether the data set is materialized or cached in memory is controlled by the user. So if the user doesn't use the cache method to cache the data set, then what happened is just like Python, uh, the execution actually is going backwards. If we want to this result, so if the user issues some action on the RDD, try to collect the result or to store the results, then we have to calculate the result, right? So the user can see it, right? So only when those actions occur, then the Spark will backtrack from the previous RDD or the existing RDD to go through those process and only store the final one in the memory. Okay, so therefore, those temporary results may not be stored in the memory. Okay, only the final result or the result that requests to be cached will be materialized and become the real data set stored on the shared memory. Okay, all right. Actually, many script language doing the similar thing, right? So they can do more runtime optimization and to only compute when it is necessary. For Spark, again, it's the same. Many techniques are borrowed from um, all those other programming languages or compiler techniques. Okay. The point is whether it's RDD is actually controlled by the user. Okay. All right. So let's just use example to illustrate what we mean. Okay. So for example, imagine we have a log file. It's very huge, right? Contain lines of error messages. And as a user, we want to analyze this log, right? To, for example, figure out the count for a certain type of error or other data analytics tasks. Okay. What happened is, of course, first of all, we have a cluster and install the Spark framework. And you can see there's a driver and worker, pretty much the same as MapReduce. The driver is the scheduler. The worker is the process that launch on each machine to do the data processing job. Okay? And for this example, first of all, we would like to read out the data from the file system. Okay, and like before, it's a data set called lines, and each line is an element in this data set. Okay, and this line actually doesn't trigger any computation because we haven't involved any action yet. Okay, action is some operation that have to generate the result. Okay, and line is just some temporary data set, so it won't trigger an action. Okay, and the next line is we will for each line, right? This means that for each line in this data set, we will apply the filter operation so that only the line start with arrow will be kept in this arrows data set. Okay, so after this statement, supposedly we will have a subset data set of the lines. Okay, this is another data set and only contain the line with arrow message. Okay, all right, and we keep transforming. Okay, so then we transform this each arrow. We try to split them into a key value pair. Okay, just trust me for now. This is what happened. The split is basically generate a key value pair. Okay, and so it becomes our messages. Okay, and then this message we will try to cache it. The reason is because later on we will iteratively analyze this data set with different data analytics purpose. So we will reuse this data basically. Okay, so since we're going to reuse this data, so we want to cache the data in the memory, right? And cache is the action because this imply we will ask the Spark to generate the message data set and store it as a RDD in the Spark cluster. Okay, so since this is an action, so this line will finally trigger the execution engine of Spark. And what it does is, well, basically, first of all, uh, oh, I'm sorry. So cache is also not action yet. It's just indicate this data set when it get materialized, it will store. Okay, so the count is the action. So even cache is not. Okay, but the cache will not only will force the data set to be stored when the data set is materialized. Okay, so count is the action because we only get the result if we process the whole data set, right? So this will trigger the Spark to start processing the data. Okay? So what it does is go back to the first line. What happened is the block is the data chunk loaded from the distributed file system. Okay, this part is sent as MapReduce. Supposedly, the Spark scheduler also will ask the Hadoop file system master to figure out where is the data and schedule the task to the data to reduce memory transfer, the network transfer, okay, the data transfer across network. Okay, and then after we identify the data, we launch the worker on the server with data. Then we will issue those, we will package those functions as a program, as a task to run on the worker. Okay? So of course, the worker will read out the data and do the filter, do the mapping, and generate the cache messages, right? And the cache message will be cached. So the driver will notify the worker to cache the result on his memory. Okay. And as you can see, this is a distributed memory because it all depends on which part of the data you processed. Then you will just responsible for caching that part of the data in its local memory. Okay. Okay. So after we cache the data, then when we do the count, the driver will generate the cache message, will generate the value of count by processing the data in the cache. Okay, so far, even though we have this memory layer, but what it does is exactly the same as MapReduce because the data still has to be read out from the disk, right? And the memory we are not reusing yet. So since it's not reused, so we didn't save any time. So if you only process the data once, Spark doesn't help you anything. But if you're going to reuse the data, for example, now we need to filter the message with bar and try to count how many arrows like this in our log. This task will process from the cache. It will not redo all those things, right? This cache message will, or this count will be directly computed from the data set stored in the cache. So it can skip over all those previous steps. So that's why Spark will be much faster for the iterative processing. Okay? In contrast, if this is a Hadoop, is a MapReduce system, then every time you do this, you have to read out the data from the file system and go through all those things. So it will be very slow. Okay. All right. So so you can see if you just repeatedly using the cache data, then your processing time will definitely much faster than the MapReduce framework. Okay, so that's why when people try to start doing machine learning or interactive analysis, they prefer to use distributed system like Spark instead of MapReduce, because the data can be reused and can be stored in memory. And it's better than a single machine because you have, right, depends on the size of your cluster, you are able to handle a larger volume of data, at least larger than the size that can be only handled by a single machine. Okay? So for big data analysis, people will use a solution like Spark. Okay? All right. Okay. So this is what happened uh, inside the Spark framework. And finally, is the fault tolerance, as we mentioned. This part is very easy to do. All it does is to remember remember the code, remember the transformation function. So every time, as I said, if there is a failure occur, some of the RDD is missing, you can always follow this trace to regenerate the result. And this technique is actually called the lineage solution. And it's also not new. As a matter of fact, the traditional database also often implement this kind of solution to do the fail recovery on a single machine, because even with a single machine, it could have some failure, right? And then the database sometimes do need to recover the content that cache in the memory. So this technique has been used before in database, but Spark also borrow it to his system and to make sure the RDD is resilient to failures. Okay. All right, so that's the secret of Spark. Okay, so you can see it's very similar to MapReduce, but it has the ability to cache data in memory. So it can provide a more diverse application or data processing, including the SQL query, right? Because SQL query usually is an interactive data analytic jobs. So with memory, then we can very quickly return the result to the user. So it's possible to do interactive data analysis using the SQL language, unlike Hive. Hive is also a SQL language, but it's not designed for interactive data analysis. But Spark SQL, it can provide interactive data processing. Okay, and also string processing. Okay, right? String processing means that it's basically online processing. So again, you have to do it very, very fast. And with Spark, the data could be temporarily stored in the memory layer. So it's possible to even support string processing. And machine learning, of course, because it's an iterative algorithm. So if you can cache the result, you can accelerate the iterative algorithm. And finally, graph. Okay, graph database. Graph database is a special type of database, and for graph database, usually you have to traverse the graph in order to resolve some of its analytics jobs. So traversing graph involve random access and involve have some data reuse pattern. So it's also could be supported by Spark. Okay? More so, right now, Spark also provide the solution for deep learning, like TensorFlow. So Spark solution is called the SparkNet. If you're interested, you can look it up online. You will see SparkNet or maybe even other deep learning framework that enable distributed training through Spark, because Spark itself is a distributed computing framework, and it doesn't care what's operation or transfer function you try to do, right? So you can use those to build a library for deep learning as well. Okay, so Spark is really powerful, and even today, as I know, many company deal with big data problem, they are still using Spark. Okay, so as we mentioned about the trend of the big data, right? So MapReduce is kind of replaced by Spark. But if your data set is really huge that cannot even fit into a distributed memory, then you still need to rely on MapReduce to reduce the size so that you can use Spark to take over and do those more complex data analytics jobs. Okay. All right. So that's it for Spark. Okay. All right. So it's also we are also about the end of this lecture. So any questions?